equal as well.
But we already showed that, right?
Yeah, we already showed that. They're equal. But only at this t, t. So, but actually, this we can use a more general input. So the two integral curves, because they are maximum interval. No, let's use this input for any u. They're the same for arbitrary u from So right now it's just a matter of rewriting them in that notation we're not familiar with. Yeah, so how could we rewrite this? These two integral curves, because their intervals are identical, right? Of course, the corresponding integral curves will be identical. Yeah, so for any u from this interval, because this interval is same as the other interval, so anyway, we'll just use this interval. So for any u from this time interval, they are identical. These two curves are the same. Can we rewrite this into the notation I just introduced? What is how do we write it? This one. Phi, we put S here, right? U here. X. Yeah, try to write this one into the notation of this form. What is what do we put here? Yeah, so let me know.
T there, right?
Yes, yeah, T is here.
And then you put U
What?
there.
Yes.
And
then
like the phi of that guy.
yes, yeah.
There.
This quantity, right?
Right.
Yes. Okay, STX, yeah. Yeah, that's this in this notation. That in this notation. So they are the same. So you see, from here to here, it's just a matter of notations. Yeah. It's clear and satisfies the semi-group property from ST, TU, and see the same as SU, right? Got this form. Yeah. So in this theorem, basically we just show this curve and that curve, they're the same curve. So in the new notation, this is the same. So you can imagine for the continuum mechanics, if there is a certain part in the, for example, we look at the fluid mechanics, we limit ourselves to a set of x, right? A set of x maybe, because if you have a set, that could be a form, then that can be, this is a set. So let's look at certain part. So we can try to interpret this as but it's not just a one point, right? It's a set of points x. So you can try to imagine the m. Yeah. So M is from where? From Rn. Just a bunch of, because each x, each point, each element of M is from Rn, right? So we just imagine there's a this region, this region in certain form, right? Certain form, we take a set of x. So for this region, what does that mean? You can also imagine this as fluid mechanics. In fluid mechanics, this is just in a certain fluid. You just focus on a certain portion of fluid, right? For this, but then it can deform because this is, for example, at when time is s, right? When time is s. Later, at time t, so this form, initial form, will become a different form. So we can draw the picture. It may be something different. So that's the shape, right, of this M, but at another time. Yeah, so we just look at this quantity. Then this one, if you use this, so that means at this time we have this, we interpret this, right, for the initial data. This means at this time we have this as the initial state, right? Remember that notation? We look at this as this S, as this initial time, we have this state, right? But now we have, at this time t, we have this state, right? Yeah. If you have question, right now we have at this time t. So this is a time s. Time is s. Right now time is t. At time t, the form becomes now this one. So that's like the initial condition, new initial condition now, right? You can view this as the initial condition, but as time goes on, it can deform into another shape. So what is the, so for example, the last can be, use this as the initial condition. This is the notation we use. So at time t, this is the status, right? At time t, this is the value. So that's actually initial condition. Yeah. So for this initial condition, we look at time u. So you see the form is determined by this now. Yeah. So the form, so it is, because x determines the position, right, of a point. If x changes, the set of x's are different, that means the shape is different at a different time. So now the shape or position will be determined by this. So just a geometrical interpretation of our, that theorem. So this just means the state using this intermediate state as the initial condition, right? And then you get a time, next time, the shape or position. But the theorem says this is same as the same directly without the intermediate, using this as the initial condition. We can also arrive at this state. So it's just this notation. Phi using S at this state, when S, that's X, right? At this time U. So it doesn't depend on the intermediate state. So you can imagine this goes from S to T, from T to U for another time. But this final state can be written in terms of S directly, right? Skipping the intermediate state. So they're the same. So it doesn't depend on the intermediate state. It's the semi-group property. Okay, so in short form, it's just this composition. Right, if you from S to T, and then from T to U, it is same as from S using S, the initial data at S to calculate U, right? To calculate the state at U. Yeah, so it doesn't matter if you skip that intermediate state because they change continuously. Yeah, so that's the summary of the theorem. And this theorem can be generalized, right? If you have many intermediate states, doesn't really matter. So you can just use that initial state. You can calculate the final state, phi at U.